Here we are, partway into our discussion of how it might be possible to make a computer learn something. Now let's face it, we're pretty good at learning. And on top of that, if you remove the skull, all you find is neurons in there. Our heads are stuffed with them. So it would seem that if we're to make a smart computer, one that can learn something, we ought to think about mimicking biology. And a great deal of effort has gone into mimicking neurobiology over the years, and today I want to tell you about it, so by the end of the hour, you'll know how to construct your own neural net, and you'll know how to criticize someone who offers to sell you a magic box that uses a neural net to predict something. So first of all, let's look at a little bit of naive biology and reflect a little bit on what neurons are like. There are lots of different kinds, but this is naive neurobiology, so we're just going to talk about the standard kind. And like all cells, there's a cell body with a nucleus inside. But in contrast with most cells, there is typically a long protrusion called an axon. And an axon divides in two relatively infrequently, but sometimes, but they do divide. That division is called a bifurcation because it's a division into two parts. On the other end of the neuron, you have a whole lot of things that branch off like so. And these things, in contrast to the axon, do nothing but branch like crazy in general. And that part of the axon, or that part of the neuron, is called the dendritic tree. And so the dendritic tree creates a huge number of places that downstream axons can connect to. So a downstream axon, it's the business end of a neuron off there, out the door. It might come in and find a place on the dendritic tree with which it wants to connect. Now it isn't quite that simple, because the nature of the connection is such that that downstream axon gets a little bulb on the end, and there is a little space between that downstream axon and this upstream dendrite. This is filled with little vesicles, the neurotransmitters that get dumped into that synaptic space. And when there's dumping of the vesicles into that synaptic space, it excites the dendrite, and if there's enough cumulative excitement on the dendritic tree, then what happens is that a signal, a spike, propagates down the axon. So that's a little naive biology, and there are some aspects of it that we should, right away, take note of. Number one, there are the synapses. And some of these synapses are thought to be more important than others. That is to say, they exert more influence on the performance of the neuron. So we have a kind of notion of synaptic weights. Some of them have a higher influence or higher weight than others. Then the next thing we need to take note of is there's a sort of cumulative effect. Cumulative. That is to say, all that stuff that's coming in on the dendritic tree is somehow added up or combined or put together with some function. Who knows what it is, but there's a kind of accumulation of stimulation on this dendritic tree, which leads to a decision about whether that spike goes down the axon. It either does or it doesn't, so there's a certain all or none phenomenon here, which is another way of saying that the spike either goes or it doesn't go. And those are three handy observations. Those are three knee-jerk observations. There's a lot more you can say about what goes on there. In fact, you can take a whole complicated course on what goes on in a single neuron. And you'll talk about sodium and potassium and gradients and refractory periods and all that sort of stuff. But this is all we're going to do. It's the only thing we're going to take note of today, these kinds of characteristics. And now what we're going to do is we're going to say, OK, given those kinds of characteristics, how would we make a model of it? Because it's MIT, after all. We make models of everything. That's what MIT is all about. So let's make a model of this little biological element. Well, let's see. First thing we're going to do is we're going to have some inputs. We'll have input 1, and it's going to come into a multiplier and get multiplied by some weight, weight sub 1. And then we might have lots of inputs. Input n will get multiplied times some weight n, like so. Oh, what have we done so far? Well, we've got number 1 kind of modeled. That's that part there. Next thing we have to do is we have to have some way of combining all of these influences, all of these products of the weights times the strength of the input. So what we're going to do is we're going to run all those guys into a summation box. So there's a real big modeling decision that we've made. We're going to just take the sum of the inputs. And there might be many of those. So let me draw a few more arrows here. Next thing we need to do, though, is we have to say, well, the output is not proportional to the input, but rather it's an all or none kind of phenomenon. So we're going to have to run the output of the summer through a thresholding box. All right? So here's the function that's performed by the thresholding box. There's going to be 0 output until we get to some threshold, and then we're going to put out a 1. So the output here is either going to be 0 or 1. So we might as well say, since that's going to be the input of the neurons downstream, that the inputs are also 0, 1, either 0 or 1. So now we have a model of a neuron. It's a naive model. It doesn't take into account much about what real neurons are like. Nevertheless, it is a model, and we can ask what we can do with it. Well, of course, one thing we can do with it is that we can put a whole bunch of these together in a big can and stir it up and see what happens. So there'll be some elements here. There'll be some neurons in here, and some of them will take an input from the outside. There's x1, here's xn, and it goes in here and finds some other multiplier, and so on. And then there'll be some summation boxes, and there'll be these weights, there'll be other weights. And then there'll be these threshold boxes, which I've made look like that, and they will produce some outputs for this system, like so, and we'll call these outputs Z1 through Zm, having already used up n. So there it is. There's a neural net, abstractly speaking. But nevertheless, it's enough of a notion that we can now say that the output vector, that's an output vector, right? There are a whole bunch of z's. The output vector is equal to some vector function of the inputs, x, and what else? Well, the weights, right? It will depend on the weights. It also depends a whole lot on the structure, but for a fixed structure, fixed way of arranging the neurons, all that the output can possibly depend on is the input and those weights. So that's Z, the output. Now, of course, if we have some training samples, then we have some desired outputs for particular inputs. And we can write that down, too. We can say that the desired output, D, also a vector, is equal to some function. But now we don't care about the weights. We just want a particular output given a particular input. So that's going to be some function of G, some function G of x. And now the neural net problem is easily stated. We want to bring f of x into alignment with g of x. That is to say, we want a set of weights that make the actual output the same as the output that we desire. So that's simple, right? That's, at least abstractly, a simple idea. Yeah, it's simple. Why don't we just go home? Well, first of all, we need a few things. Number one, we need to know how bad we're doing. Or, if you're a more optimistic type person, how well we're doing. So we need some measure of how good our set of weights is. And that must be a function of the difference, or it must be some function of the desired outputs and the actual outputs, right? Okay? So we need a performance function. Just for fun, we'll call it P. So P is a function of the desired outputs and the actual outputs, like so. And the one we're going to use today is this one. We're going to say that the performance is equal to, I don't know, D minus Z, the difference. Let's take the magnitude of that, and let's multiply it by 1/2, and let's square it. Where the devil did that come from? Did God say that that's the right way to do it? You don't think so, Leonardo? Why do they make that the performance function?
You wanted to minimize distance squared, and you're normalizing. You're trying to minimize the distance to a line.
So did God say this is the best performance function to use?
No, but you.
It turns out to be. It turns out to be. It turns out to be a little more than adequate. It turns out to be good. It turns out to be mathematically convenient to use this particular metric. And that's not a bad thing to have. After all, if we draw a graph of this, if there's only one D and one Z, so it isn't a vector, then the graph looks like this. So we'd like to minimize that quantity. Now you can think of, but there must be some imprinting early in 1801, because I don't like to think about minimizing stuff. I like to think about maximizing stuff. So we're not actually going to use this as our performance function. We're going to use this as our performance function. I'll put a minus sign in front so that the curve looks like that. And what we're trying to do then is we're trying to maximize that performance function. It can only be negative. We're trying to maximize it. When it's a maximum, when it's at maximum, it's 0. It's just the difference between going uphill and going downhill, and I like to think about going uphill. Well, now we're on the way. All we have to do is find some way of finding the best combination of W's that do the right thing to that performance function. So let's have a look at the world's simplest situation, where we just have two weights in there, W1 and W2. Now, for those of you who climb mountains and stuff, you'll recognize that I'm going to draw a little topographic map of the performance function, and I'm going to assume that it looks like that. These are equiperformance lines. All right? And now suppose that we start off with some combination of W1 and W2 handed to us by a random number generator, say. And let's say that we start off right there. Now we've already had a good part of 6034, so we know what to do, right? This is my God, I've even talked about mountains. It's a hill climbing problem. So we can do what we learned about real early in the subject. We can do a hill climbing type depth first search type thing. And if we do that, what we do is we say, well, I can either move north, I can move west, I can move south, or I can move east. And plainly, moving east is the winner, because that's taking us uphill. All right? So if that were all there were to this, then we could all go home and sleep. But it isn't. Oh, we can sleep anyway, I guess, come to think of it. But this isn't all there is to it, because the trouble is, if there are lots of W's, this becomes a hugely high-dimensional space. So this idea of trying one move in each direction doesn't work very well. So we have to think of something better to do. Before we get to But by the way, nevertheless, this is, well, wait a second, halt. We forgot that we don't have any thresholds in here either in our model, so we need to have some way of altering not only the weights, but I guess come to think of it, up in here, we can have thresholds that we can adjust as well. But there's a trick that will help us to get rid, that will not just help, enable us to get rid of thinking about the thresholds. So let me tell you about that trick. What we're going to do is we're going to add an extra input here, like this. It's going to have a multiplier on it like this. It's going to be permanently connected to -1. And it's going to have a weight coming in of W0. So we got W0, W1 through Wn. And what we're going to do is we're going to make W0 equal to that threshold. And if we do that, that sort of subtracts T off of this thing. So instead of firing at T, we got to fire at 0. So what we're going to do then is we're going to replace our original threshold function by one that looks like this. Same thing, only it triggers at 0. But now, you see, we've rendered that thing as a weight, and we can adjust that weight just like any other ones. We can hill climb it or whatever we want to do. So we got a series of tricks here, and this is trick number, well, let's call this trick number 1. Now, over here, we decided that ordinary hill climbing won't help much because there are too many dimensions, but we've all taken 1802 or something like that, and we know what to do with a situation like this where we're trying to climb around in some space, and we're trying to find the highest place we can get to. We know what to do, right? We have the method of, what do you think, Casey? You do what? Yeah, you go up perpendicular to the contour line using the method of what? Gradient. Now there's only two possibilities, ascent or descent. And I've arranged to go up, so this is gradient ascent. We're trying to cross those contour lines perpendicularly, so we got gradient ascent. So instead of just trying out these northeast, southwest deals, what we can do is we can try to go in that direction. And to go in that direction, we can just use good old 1800 something or other and say that delta W, the difference in the weights that we want to use, is equal to, let's take the partial derivative of the performance function in the x direction, multiply that times a little vector I in that direction, plus the partial of the performance function with respect to y, plus a unit vector in the up direction. And so that becomes our delta W. All right? Except that maybe we want to put a little rate constant there, like so. So that's the rate constant. Now let's see if this makes sense. We want to make sure that the math makes sense intuitively. If I go in this direction, and if that partial derivative is big, that means I'm getting a lot of bang for my x buck. And so that sounds good. I want to go a lot in that direction. On the other hand, if I'm not getting very much out of going in the y direction, as I am not here, that means that the partial derivative will be small. That means I don't want to go much in that direction. I want to go mostly in the x direction, only a little bit in the y direction. And that's what that says here. This partial is big, this partial is small, so I'm going to end up going sort of in that direction. In fact, my arrow is a little bit too severely in that direction. It'd probably be more like that, crossing the local contour line. So that's what we're going to do. We're going to use gradient ascent. Except that we can't use gradient ascent. There's something about our problem that isn't like what we had in 1800 something or other. What's the problem? Well, what is required before you can use gradient ascent? Leonardo says we have to have a smooth, continuous function. And this is anything but smooth because we got that step function in there. So this method will work. But anyhow, this is a good idea, and we'll call this insight number 2. Oh, but wait a second. We can fix this, actually, because God didn't say we had to use a step function, we could use a smooth function. So why don't we come back over here and make yet another adjustment. So instead of, we've got that, but we want to adjust it again. And what we want to do is we want to have a threshold function that's not sharp like that, but rather sort of on the smooth side. I don't know, let's use all of our colors while we've got them. So maybe what we want to do is have something that is the same on the ends, but which is a little bit smoother in going through 0, looks like that. That would certainly do a job for us. And in fact, the function we're going to use is 1 over 1 plus e to the minus alpha, where this is alpha. Now, did God say that was the right? It does have that shape, right? So if alpha is very large, then e to the minus alpha is 0, then it's 1. On the other hand, if alpha is very negative, then it's 1 plus some big number, that's 0. And if alpha is equal to 0, then it's 1 plus 1, so it's 1/2, just like I drew it. But there are lots of functions that have that property. Scylla, why did I use this one? Did God say I should use this one? No.
But you might have used
But it might turn out to be,
the simplest or the best.
why would it be the best? Because it's mathematically convenient. Yeah, that's right. Maybe it'll turn out to be mathematically convenient. So that's insight number 1, that's insight number 2, and this is insight number 3. And impossible problems are often solved when you have 3 insights in a row. And this one is in fact solved when we have 3 of those insights in a row. So now I could just write down the formula, and you'll see the formula in other venues, but I refuse to do it because what I want to do is I want to work my way through the world's simplest neural net that illustrates the necessary ideas. So here's what the world's simplest neural net looks like. The input, there's just one input, x. It's multiplied times some weight, W1, and that produces a product, P1, and that goes into a threshold box, which is this function here, which looks like this curve here. And since it sort of looks like an S, we're going to call that a sigmoid function. It's a sigmoid function. Did you ever hear about a sigmoid function before in this course? It's exactly what we use as our thresholds on quiz grades. So we're going to use a curve that looks like that. And then out here comes y, and then the y gets multiplied by another weight, W2, and that produces P2, and that goes into another sigmoid like so, and produces Z, and Z goes into the performance calculating box, and out here comes P, which is equal to minus 1/2 the desired output minus the actual output squared. And now since I've only got one thing and not a vector, I write it as a scalar. So what I'm assuming is that I have some samples with desired values, and I can observe Z, the actual values, and I want to bring them into conformity by doing these partial derivatives and stuff, and then making the necessary adjustments to the weights. Simple, right? Now, this is where I've got to do a little partial differentiation and stuff, so you down here in front are in charge of making sure I don't make any mistakes. And if I make any mistakes, well, I'll hold you accountable. So I don't know what to do with that, actually. What a mess. Well, let's see. According to the formula on the middle board, let me forget the rate constant. We can put that back in later. But according to that thing there, I need to calculate in order to figure out how much of a change to make to these W's, I have to calculate the partial derivatives of that performance function, and you know, geez, I better make an adjustment here before it's too late. X is actually W1 in my diagram, and Y is actually W2 in my diagram. So what I want to do is I want to calculate those partial derivatives. So I have partial of the performance function with respect to W1. Anybody work that out in their head? Oops, wait a minute. What have I done? Oh, there, sorry, W2 here. Let's start with W2 since it's closer to the output. Partial of the performance function P with respect to W2. How do I do that? I could throw up my hands and give up, but no. I went to MIT too, and I know about 1801 stuff, and I know in particular about what? When you want to compute a derivative and there's a whole bunch of junk in the way. Gosh, I feel all tied up. I feel like I am shackled by what? The chain rule. Thank you. Okay, so the partial of P with respect to W2 can be written as the partial of P with respect to Z times the partial of Z with respect to W2. Okay? Well, here's P and here's Z, so I can take the partial derivative of that pretty straightforwardly. Let's see, I bring the 2 down, that cancels with the 1/2. Then I've got D minus Z. Then I take the derivative of the insides, which is -1, which cancels my -1 out here. Oh, I think we can do that in our head. That's just D minus Z. That's the partial of P with respect to Z. Okay? So now, the next thing I have to do is calculate the partial of Z with respect to W2. So it's the partial of Z with respect to W2, but this box is in the way. In fact, P2 is in the way. So I can use the chain rule again, right? So instead of calculating the partial of Z, so in order to calculate the partial of Z with respect to W2, I can write that as partial of Z with respect to P2 times the partial of P2 with respect to W2. Okay? And now let's see, the partial of P2 with respect to W2, finally something easy. So now we can write this out as D minus Z. We still don't know about that guy. But we do know that the partial of P2 with respect to W2, oh, that's just Y. So bingo, we've calculated our first partial derivative. Now for the hard one. Well, it's not super hard, but it's a little more involved. The partial of P with respect to W1. Well, we can start off just the same way. That's going to be equal to partial of P with respect to Z, partial of Z, partial of W1, not W2, partial of Z with respect to W1. So that partial of P with respect to Z, we've already done that. That's D minus Z. And now partial of Z with respect to W1. So I've got Z here, and I've got W1 way over there. So I better take my next variable, P2, and stick that in there and do the chain rule again. Partial of Z with respect to P2, partial of P2 with respect to W1. I've got to keep my indexes right because I'm trying to get the partial of everything with respect to W1 now. Okay, so let's try working on partial of P2 with respect to W1. Writing the stuff I've got carried over, D minus Z, partial of Z, partial of P2, partial of P2 with respect to W1. P2 with respect to W1, well, Y is the variable I'm going to have to use. So I'm going to say that this one here expands to partial of P2, partial Y, partial Y, partial W1. Oof. Okay, so I've run out of room over there. Let me write the next step here. D minus z times partial of z with respect to P2. Partial of P2 with respect to y. That's P2 is the product of W2 and y. So the partial of this guy with respect to this guy is just W2. Now we've got partial of y with respect to W1. Oh, one last chain rule element here. Here's P1 in the way. So it's that partial of y with respect to W1, that's going to be equal to partial of y with respect to P1, first product, times the partial of y with respect to W1. That's this product here, right? So I want the partial of this with respect to this. That just must be x. So I left out one small step that we can all do in our head. Now I've got the solution right there. So that's it. Except we haven't let the math sing to us yet. But we will. Trust me, we will. The reason we're not quite ready to let it sing to us yet is we still have a few annoying partial derivatives in there. So here's the partial of p with respect to W1, and we got these two partial derivatives in there. Partial of y with respect to P1, partial z with respect to P2. Up in here, this one, that has one of those same partial derivatives in it. So we're going to have to come to grips with the fact that we're going to have to figure out the partial derivative of the output of this box with respect to its input. Okay, so draw a line through there, get back on the train, because that math is done, except we have to let it sink to us. Next math we have to do is we have to figure out what those partial derivatives are that are still annoyingly in our formula. So, just because it's a different problem, let's use a different board. And let's see, what we've got is that threshold function is b equals 1 over 1 plus e to the minus alpha. And what we need is the derivative of the output with respect to the input. So it's the derivative of beta with respect to alpha. So, I don't know, let's see. Derivative of beta with respect to alpha is equal to what? Anybody do that in their head? Probably not. I can never do these quotients. Somehow it was one rule I never quite learned. So, but the first thing I do is I get rid of the quotients. So that's equal to the derivative with respect to alpha of 1 plus e to the minus alpha to the minus 1. Everybody comfortable with that? Now I got rid of my quotient because I could never remember that rule. Now this could be hell, but let's see what happens. This is equal to, oh my God, what is it equal to? 1 plus e to the minus alpha, and that exponent drops by 1 to minus 2. And we bring the minus 1, we got a minus sign up there, minus 1 in there, so that's there, right? Now we got to differentiate the inside. So the derivative of the inside is the derivative of e to the minus alpha. And the derivative of e to the minus alpha is e to the minus alpha. And then there's we got to differentiate that, and that's a minus 1, so now that got rid of our minus sign. So if we'd forgotten a minus sign, we'd just be just as well off. Oh, wow, well, now we got to play with it a while. It's going to take all of Saturday afternoon. We're struggling to work this all out, and we haven't got something simple yet, but we can play with the math, and maybe by dinner time we'll be done. So let's see, this can be written as e to the minus alpha over 1 plus e to the minus alpha squared. And everybody happy with that? Now, using the law of addition and subtraction, we can add 1 with impunity as long as we subtract 1. All right? So let's see. So let's take one of these guys outside, like this, and we'll multiply it times the stuff inside. So let's see, that's 1 plus e to the minus alpha over 1 plus e to the minus alpha. Wait a minute, you said I forgot the minus 1 over there. That's okay, I'm going to put it in right here. Minus 1 over 1 plus e to the minus alpha. All right? And there it is. Magic. Because what's this guy? That's beta. So if that guy's beta, this guy must be beta too. And well, that's 1. So the whole works is equal to beta times 1 minus beta. Isn't that cool? That's because, what was the phrase Silly used? Mathematical convenience. Yes, we chose a mathematically convenient function so that the derivative of the output with respect to the input is expressed in terms of the output itself. Let me say that again. Usually if you have x as a function of y and you differentiate, you get a whole bunch of y's in the answer, right? This is cool because we differentiated it and we got differentiated beta with respect to alpha, and all we got out was betas. It's cool. So with all this little stuff here, all we have to remember is that part right there. So it doesn't matter when I go back and cover up the board. Because now we can go back and say, oh, this one, that must be z times 1 minus z. And there's one of those down here, too. And let's see, this one must be y times 1 minus y. All right? And now we can let the math sing to us and say, well, what do those partial derivatives actually depend on? Let's look at W2 first. That partial of the performance function with respect to W2 depends only on d minus z, z times 1 minus z, and y. Or to put it in terms of what variables it depends on, what variable values it depends on, W2 depends only on z and y. Okay? Well, what about W2? This partial here depends on d minus z. Oh, but I already calculated that. It depends on partial of z with respect to P2. I've already calculated that. It depends on W2, and it depends on y, and it depends on x. So the value that we have to calculate for W1 depends on W2, depends on y, and it depends on x. And that's all it depends on other than things we've already calculated. Okay, now the math is beginning to sing a song. What if there were 100 of these all lined up? What would the last one depend on? 99 other things? Nope. Just depend on stuff we've already calculated and stuff in the vicinity. So that's the magic of this algorithm, which is, by the way, called the backpropagation algorithm. Because you start calculating the w's that are close to the output, and as soon as you've got those, you've got just about all the information you need in order to go one step back and calculate the w's in the next row, next column. And then go back to the next column after you've done that, and all the way back as many layers, as many columns as you have. So if you've got 100 columns, then the amount of calculation you have to do in that last column is just the same as the amount of calculation you had to do in the middle column or at the end. It's a local computation. So guess what? For a fixed number of neurons in a column, it's linear in the number of columns. Yes.
How does this deal with feedback loops?
It doesn't. The question is, how does it deal with feedback loops? There are a million variations on the theme of neural net, and some of them do have feedback loops, have outputs that eventually go back into their inputs, and we're not dealing with that particular kind. So that's it. That's the intuition. You calculate the stuff in one column. It's almost all you need to calculate the stuff in the column preceding it, which is almost unique back here. It's a linear computation in the number of columns. Backpropagation algorithm, which lay undiscovered for many years while people were trying to figure out how to make models of neural nets. So it's that impossible equals 3 steps. There were just a few things that had to be kind of get sorted out and put in a row before this backpropagation algorithm was discovered. It was considered a serious discovery at the time it was discovered. So that's wonderful. Now we know how neural nets work, and we can forget about the rest of AI. And that's what a lot of people thought too. But then, once you understand it, you have to go back and ask yourself questions about it. And that's the ask why 5 times business. So here's one problem. The ask why 5 times business, by the way, goes back to something called total quality management. It's one of the many package mechanisms for doing management that was based on some work done by Deming for the Japanese just after the Second World War. He went over there at MacArthur's request and fixed Japanese manufacturing. Before Deming arrived, Japanese manufacturing was mostly, if you said Japanese, that meant junk. After Deming got through it, a few years passed, Japanese meant high quality. But one of Deming's pronouncements was, you should always ask why 5 times. Don't take the knee jerk. Somebody comes up to you and says, well, we got a new method for calculating, for predicting stock market prices. It uses a neural net. Your reaction should be as if the person had said, we have a new mechanism for calculating stock prices. It uses a Ouija board, or it uses magic, because that's what they're doing to you. They're trying to impress you with some technology, which you now understand. What is the technology actually doing? That's the first question we have to ask in our 5. And what it's actually doing is it's got some desired outputs and it's trying to contort the weights to give you actual outputs that are like the desired outputs. So it's fitting a curve. So you've got lots of ways of fitting curves. You use the Fourier transform. So you have to say, well, why is this better than a Fourier transform? Why is it better than any one of many other mechanisms for fitting a curve? That's problem number 1. Problem number 2 is, so you got a problem involving playing the ponies at the racetrack. How do you encode all of the parameters in your input vector so as to reflect the properties of the problem? Usually that's the hard part. The curve fitting part turns out to be easy once you got that initial input representation right. And that's not captured by neural net theory. That's still left up to you as the practitioner. But I might have another little demonstration here that will illustrate 1 or 2 other problems. Now, this isn't exactly the kind of neural net we just looked at, but it's very similar in nature. There are some weights. They need to get adjusted. And the idea is to approximate that red curve with this neural net mechanism. So the sample points are the little red dots there. So as we step through this, we ought to find ourselves with an output curve, that's the green one, that eventually brings itself into conformity with the red one, with those red dots. I'm getting tired of this. Let's do some multiple steps, like 20 steps. Let's do 20 more. Let's do 20 more. Well, there's 110 steps. Let's do 20 more. And you can see that the new green line, the latest green line, actually is getting pretty close to going through those red points. But you notice there's another little problem. There's another little feature up here. You notice how that guy's beginning to bend like crazy in order to conform to that? And let me try to go 100 steps more. Okay, there's 100 steps more. Now it goes through there, but right here, it kind of has to bend itself real hard, and it'll do it. But you say, well, I'm not sure it really should be doing that because I'm actually trying to fit a smooth surface to these sample points. This is the so-called phenomenon of overfitting. You're trying so hard to contort yourself to the sample points that your values in nearby places are often highly distorted in order to kind of, as a contortionist, to get into that space. So that's a problem. So that's problem number 3. But this was pretty slow, so let's reset that guy. And I used the 0.05 rate. That's that multiplicative factor that we ignored in the development of the math. Now, when we put that back in, we can use various rates, right? So this was too slow to converge. So let's try this one. And I don't know, let's try our first 20 steps. That's good. You notice it's converging, or it's getting itself to conform much faster. That's good. Well, that really worked well, but since that worked well, let's go to 25. Restart it again. Go through our first, just 10 steps to see how fast it goes. So what's going on here? Uh-oh. Well, let me try that again. So let's go to 100 steps. Well, maybe there's something weird about that. Let's just... Oh. Well, should I apologize? No, I shouldn't apologize because this illustrates something. What is it illustrating? What's gone wrong? Leonardo's on top of stuff today. What's up? What do you think?
So your rate is too big.
The rate is too big.
You're basically missing the hill over every time. You're just going.
You're overshooting.
You're overshooting every time.
So you got a feedback loop here. And what kind of feedback loop is it? It's a positive feedback loop. So this thing has begun to oscillate. It's begun to just blow itself apart. So yet another problem you have with neural nets is picking or adjusting as you go the rate constant so that you don't get into this kind of violent positive feedback situation where instead of converging on an answer, you just blow yourself to pieces.